Okay, so hello, my name is Michael Unser, and I'm a professor at the PFL heading the Biomedical Imaging Group. So today I will give you an overview of biomedical image reconstruction from the foundational aspects of system modeling and direct reconstruction to sparsity and learning-based approaches. So my co-author is Dr. Pol del Aguila Pla from the Lemanic Center for Biomedical Imaging. Will show you how to concretely implement some of the algorithms that I will explain to you. So as you know, imaging is a critical tool in biological research and medicine, and also most imaging systems really heavily rely on sophisticated signal processing to reconstruct the images. And also the design of this algorithm has been a topic of research since literally the 1960s. So it's relatively mature, but as you know, in the past few years, machine learning-based approaches have shown impressive performance, specifically on image reconstruction problem, and therefore have triggered a new wave of enthusiasm and creativity. So now our goal now with this tutorial is to unify this body of research by identifying common principles and reusable building blocks that can be extracted from the literature, and all this for a variety of imaging modalities. So the picture that I will present is a bit stylized, this for pedagogical reasons, also because of time constraints. And so therefore I have to apologize in advance for some simplifications and omissions. Now, if you want more details, you can refer to a recent tutorial paper that just appeared in Foundation and Trends of Signal Processing. And there's also an associated library in MATLAB that's called Global BioIm, that's also linked to ERC grant that will actually be presented by Paul. Okay, so now let's jump into the subject, and therefore I have to share my screen. Now, for the outline of the presentation, so we will go progressively. So first, I'd really like to give you a general overview of imaging as an inverse problem, so just to frame it in a signal processing context, talking about different operators, so just give you the notation. And then I'll start with classical image reconstruction algorithm, and those I've labeled like a first generation algorithms. And so this is the sort of back projection, filtered back projection algorithm that is used routinely in scanners. So this is really like the foundation. Then we move on with what I call second generation methods, and in particular those that are related to compressed sensing. So it's sparsity-based image reconstruction. And so there have been a huge amount of research in the past decade. And this is also the place where Paul will intervene, because we will show you some specific examples and also like some software that will allow you to implement some of those methods. And last but not least, I want to tell you about the learning revolution, and those we have labeled as third generation methods. And now all those techniques like first, second, third generation are not disconnected. In fact, as we will see, the second generation use lots of the first generation stuff as building blocks. And now the learning type algorithms, very many, the first ones are really like sort of add-ons on classical reconstruction algorithms. So they also incorporate this first generation algorithm. And now the latest one are also like more sophisticated, not just feed-forward neural network that also involves some type of recursion. And so they very much also follow the kind of algorithms, so iterative frameworks that were developed in the context of compressed sensing. Okay, let's just start. So inverse problems in bioimaging. So really what I want to tell you about is all this class of problems where, let's say you want to reconstruct an object, and it can be something in 3D, maybe even 3D plus time. And for example, here it's microscopy, so it's a concentration of a fluorophore, and you don't have direct access to that, so you're looking through an imaging device. And because of the physics, usually you can look at it as an integral operator. And then maybe you have some detector here, and there's always noise. And so at the end, maybe when you have discretized, you can write it down as this relatively simple equation here, where you relate like the input, which is unknown, the physics, the h, and the n is some measurement noise. And of course, so the y are those discrete values that you are getting out of your scanner. And based on those measurements, you want to reconstruct this. Now, the easy scenario, and that's called a sort of well-posed problem. And usually for mathematician, a problem is well-posed when you can write this kind of equation. I mean, this here represents your measurements. And so somehow that you could have an inequality that involves also the norm of what's unknown. And so that you can have a lower bound like here. If this is the case, you can invert in some sense the matrix H. And if it's not the square matrix, you can take a generalized inverse. And if you assume that noise is negligible, you're essentially done here, okay? And end of the story, end of the tutorial, and you can go home. But of course, it's not quite as easy. By the way, there's also a poor man's solution of that. If, let's say you're in a good situation where your system matrix is orthogonal, so you can just take like the transpose, which in fact is the back projection algorithm. And in fact, historically, when people have proposed the new imaging modalities, that's usually the first reconstruction algorithm that they've proposed, which let's say is related to that. But of course, I mean, things are not quite as easy. I mean, all this formulation doesn't take noise into account. So if you just inverse, you have noise amplification. In fact, those matrices H are much too large to invert directly. And interesting problems, the ones I want to tell you about, are really ill-posed. So, the part one, I give you the foundation. Now, I'm from Switzerland, and you know what's our specialty, you know, next to chocolate. Okay, so watches. And so I've used that a little as an analogy. So let's say here, to set up the problem, we have really like to talk about the building blocks. Okay, forward imaging model. So this is really like what we need to describe the physical process where we go from, let's say, an unknown, for example, density of protons when you do MRI, to the measurements. And so now the unknown object that you want to reconstruct really lives in the continuum. And so it's the continuum X, Y, Z, so that's a space domain, and T can be time. Okay, so that's in some sense an analog unknown. And now if you want to put some math, you can say, okay, this is like a function that lives in the space of finite energy functions. And now what you have now, let's say this microscope or the MRI scanner, you can think of it as an operator that will output now a finite number of measurements. And those are obtained by applying this operator, so that represents mathematically the imager to this unknown signal, which is defined in the continuum. And really here what happens, you're going like from this continuum, in some sense, infinite dimensional degrees of freedom to something discrete, where you're only cranking out a finite number of measurements. And now, okay, what makes imaging work? Usually we assume, actually we assume that the signals here are no, the imaging operator is linear. And you all know what's a linear operator. So if we're just doing a linear combination of you know, objects here that we want to image, and then you're taking, let's say, the imaging of the linear combination, it's equivalent of, you know, just imaging any object separately and forming the linear combination after. Okay, so that this is completely standard. Also, this is important because it allows you for this imaging to be quantitative. Now, if you know from functional analysis, in fact, if you have an operator acting on a function, if the operator is linear, you can always represent the operator here by a bunch of inner products, because every measurement here is really a linear function of the signal. And so therefore, for every measurement, you can write like a physical equation that would involve here the image that is unknown, and here this mu m of r, so that would in some sense be the impulse response of the nth detector. And so here I'm being relatively general at that stage. Now, of course, if you want to set up the problem, now you have to go and study some physics. And I would also advise people who get involved in medical or biomedical imaging, I mean, study the physics, because I mean, your algorithm will be only as good as you really understand what's going on in the measurement process. And so I mean, you can do medical imaging, optics, molecular imaging there. I mean, this is relatively broad. Okay, now, as you all know, just look around, images obviously are made of sine waves. That's a typical image here. So, so images are a sum of plane waves. So you know this is Fourier analysis. And so your basic operator in imaging is the Fourier transform. And so the Fourier transform is really an operator that starts from the continuum, let's say the space of finite energy function, and also gives you a continuum in the Fourier domain. And now the Fourier operator is defined by this here, where we are doing here an inner product between an image here and the plane wave. So the plane wave was just this guy here, okay, so that complex plane waves. And then if you have this Fourier transform, which we denote by a hat here, you have a reconstruction formula, which is the inverse Fourier transform, so that given this continuum of frequencies here, if you know those, then if you do the summation with all the sinusoids here over the whole spectral domain, which is RD as well, you can reconstruct your image. And in some sense, this fits in what I was saying you on the first slide, that this would correspond, let's say, to a measurement system where, oops, sorry, those measurement functions here are those complex sinusoids. But seeing is believing, and so I've given that tutorial more like to, let's say, biologically oriented people. So I like to show them that indeed the images are some of Fourier of sinusoids. I mean, this is not a biomedical image, but now what we're playing here is a game, okay? We are going to reconstruct this image here using a subset of Fourier coefficients. And of course, we're using the largest one, and then we're adding more and more sinusoids. And so here, I'm just essentially using two sinusoid, or real value, just one. So that's your best approximation of this image. And now I play a little movie that we will like put more and more sinusoids. So 2 to the power 4, 5, 6, 10. And I mean, it's exponential, goes very fast. Let me play it to you again. So if you add more and more sinusoids, so at the end you get your image. But of course, you also see that if you want all the details, you need to put awfully many sinusoids. Okay, why is that relevant to imaging? In fact, if you look at magnetic resonance imaging, and here's really a physical device that was constructed by engineers and physicists in such a way that it is really measuring the Fourier transform of your specimen. And so now here I just describe maybe the principle in 1D, and that's sort of the principle of frequency encode. So you are imposing a magnetic field, you know, that will so condition the frequency of resonance of those spins. And now if you can put a gradient along one direction and you put an excitation, then things in the specimen will oscillate at frequencies that depend on the location. Now, based on this physical device, then what you can see is that the MRI machine, in fact, is doing some kind of sampling of the Fourier domain. And so it's really computing like Fourier coefficients at a given number of Fourier coefficients, Fourier frequencies that would be, for example, over a grid, but can also be over a spiral. And this is the measurements that you would be getting in MRI. I mean, this is a sort of simplified model because in practice, what you also have to do maybe is to model the effect of the coil. And so there's a coil sensitivity. And so that you will have like your Fourier, but it would, I mean, the specimen here would be weighted by a function. It's a windowing function, which represents the effect of the coil. And so that brings us to our second operator. So it's a windowing operator. So again, it's an operator that acts in the continuous domain. And to a function, it will associate the function multiplied by a fixed window W. For example, this coil in MRI. Now there's a special case, super important for imaging, which is modulation. Now, if you take this windowing function to be a sinusoid, I mean, then, okay, so you do this multiplication, and you also know from basic signal processing that that will shift the frequency, the Fourier transform of your specimen. And this is used a lot, not only for MRI, actually, it's also used for MRI, but it is used for in optics, for example, for structured illumination microscopy. So that one is really like modulating the specimen with the sinusoid of light to actually shift the frequency, the Fourier transform. Now, what is another basic operation? So the other basic operation you all know is convolution. Okay, so here's just the multi-dimensional version of a convolution integral. And here it's really an integral because we are talking in the continuous domain. We also know that H here is just the impulse response of the operator. So here, so the operator, which would be this convolution applied to Dirac impulse. And so in that case, if we wanted to, connect that with what I was saying in my first slide, this being the impulse response of my detector, I mean, here, it would just be the samples, the shifted version of the impulse response, okay? And so different shifts of the impulse response. Now, if you do the inner product, will give you like sampled version of this convolution integrals. Now, if you have a convolution, again, this also goes very well with Fourier, because if you take the frequency response, so it's the Fourier transform of the impulse response, so you know that the convolution corresponds to a multiplication in the frequency domain. And now, why is this relevant? For example, it's super relevant to optics. Now, if you have like an optical system in 2D, so let's say here an objective, it's a diffraction limited optics, the type that Paul will also describe in more details. In fact, the effect of this optics here is really like a convolution with the impulse response, but in optics you talk about the point spread function of the microscope. And now the point spread function here is given. Now this is for idealized optics here in 2D. This corresponds here. The impulse response is the airy disk, and so this sort of models the effect, the diffraction limited effect of microscope, so in fact the idea being really that if you're using optics, what you are doing, in fact, you are kind of blurring your specimen. And so maybe like as an inverse problem, you would like to unblur, which would be deconvolution. And so if you are nicely in focus, you have a very narrow impulse response. And if you're a little out of focus, you will have like a much broader impulse response. Now, the other important operator for our purpose is the X-ray transform. And so that goes with tomography. And so the transformation here is the radon transform or the X-ray transform. that actually will compute here line integrals through the specimen. And so now here, the radon transform, so it's something that takes images. And here in this case, we have like a 2D image that is indexed like along X and Y. So that would be this X here, for example. And now what we are doing with this radon transform, now we are considering many different angles and shooting X-rays or rays just through a specimen at some fixed angle. So here for a fixed angle theta, and then what one is doing, one is just integrating now the specimen along those lines. Okay, and so here you just have a vector theta that is the vector that sort of will allow you to span along this direction here, and the vector theta perpendicular, which will go like this, and so we are integrating along this ray here. Okay, so for every t defines a ray, and then we are integrating along this R variable here. And now, if you want to write it down as an inner product in 2D, you can have like the equivalent of an impulse response, but the impulse response corresponding to this detector here would just be a Dirac that has exactly the shape of this line. So it would be very narrow in this direction, and so a Dirac like this, and a constant along this direction. So that's what's written here. And so if you take, for example, here, I mean, a certain absorption map, and if you look at the radon transform, so this is now, okay, here we have a theta. So if we fix theta, like here, so we have just this profile that we see along here would be here just the magnitude of those line integrals. Okay, so that's what you're seeing here. And now what you do, you will just now turn the rays and so look at different orientation and remeasure your line integrals. And so that's the kind of measurements that you are getting in X-ray. That's called a sinogram. And in this case, as I said, the equivalent analysis function or impulse response would be Diracs along those lines. Now, what goes with those X-rays, actually the central slice theorem. So this is really the basis of tomography and medical imaging. And there are at least 5 Nobel Prize based on the utilization of that central slice theorem in imaging, including, the one of 2 years ago in cryo-electron microscopy, like Joachim Frank and Dubochet. So anyway, what we get on the scanner, because we are just measuring, I mean, those absorption maps, but a lot in different orientation. And so we get a bunch of projections here in 1D, but it could also be higher dimension, indexed by the angle here. And now there's a very powerful theorem that says the following thing. So if you measure, all these sets of line integrals, so indexed by theta, and now if you do the 1D Fourier transform of all those red guys, and that's what I call here this E hat theta. So those are 1D Fourier transforms. Or now, if you alternatively take your image and you just do a regular 2D Fourier transform, now indexed by omega. And now this 2D Fourier transform, you can also write in polar coordinates, okay? Polar, there would be an angle in the Fourier domain and a radial frequency. Now the central slice theorem, what it tells you is actually, if you write your Fourier transform in 2D or 3D, it's the same thing. If you write it in polar coordinates like that, now every ray of this, I mean, going through the origin, okay, so if you fix theta and you just go through the radial frequency like in 2D space, Now you go through the 2D Fourier transform through this line here, going through the origin. Okay, so this is exactly what's represented here. This is exactly the same as the 1D Fourier transform of this integral here. And of course, you see the idea then, because we are turning around the specimen, you will just turn this red line, and you will kind of scan your Fourier domain. And now if you do measurements at enough angles, then you know your 2D Fourier transform, and then you can, in principle at least, reconstruct your images by doing an inverse to the image, inverse to the Fourier transform. And if you do so, you get a Nobel Prize. I mean, a few people got a Nobel Prize if you are the first to do that. Interesting, I mean, it's very, very powerful theorem. And here I have a one-line proof where I just show that this formula is true for theta equals 0. Because if I just write explicitly that this Fourier transform in 2D for theta equals 0, now, so I'm just looking, you know, along this variable here, and I'm having 0 here. So that's what I'm writing here. And so I write just my Fourier integral. So the omega y here is 0. So I just have a sinusoid that goes with x. And then what I'm just doing, I'm interchanging the order of integration. So here I'm integrating first over y here. And if I do that like that, I see that this first integral is exactly, you know, integrating through the specimen along the y here, like this. So it's exactly this projection at angle 0. And so I call that P0 of x. And then here, this is just a Fourier integral, so you can just read it off. This gives you the Fourier transform of this projection. And then you can use the fact that if you rotate an image, it corresponds to a rotation in the Fourier domain, and you can generalize the argument for any angle. Anyway, why am I telling you that? Is actually my claim somehow is that the algorithm, I mean the basic operators that I just described now are sort of the building blocks of, you know, used in many, many different imaging modalities. So I just told you about tomography. Okay, so tomography, this is the radar. Now, deconvolution microscopy, that's very frequently used in biomicroscopy centers worldwide. So there's software that really tries to deconvolve images. And so here the operator to invert is a convolution. Structured illumination microscopy. So there, for example, you have a windowing because what we're doing, we're multiplying the light intensity here by an illumination that's modulated. And so we have a modulation first, and then you still have the effect of the microscope, which is a convolution. And that allows you to crank up the resolution of the microscope. Positron emission tomography, I mean, here you can also either make a link with radon transform, but you can also, for example, if you have time of flight, you can also make a link with convolution. Now, if you do magnetic resonance imaging, here I already told you it's just a matter of doing Fourier transform, maybe then sampling. If you do, for example, cardiac MRI, parallel MRI, and so this is MRI where you have multiple coils. Now, every coil acts like a windowing operator, and then all this is followed by a Fourier. And then if you still wanted to do measurement in time, so you will have like a series of Fouriers, but a long time. But the Fouriers would be, of course, in the spatial domain. Optical diffraction tomography. So that's actually, this is interesting because optical diffraction tomography is a purely optical modality. And now, if you compare with MRI, it's almost the same. It's just we put the Fourier first and the windowing after. While here we put the windowing first and the Fourier after. Now, okay, this guy came after MRI. So that means actually the clever people here wanted to develop algorithm for optical diffraction tomography. They could just take the inspiration from MRI, but usually they didn't know MRI. But let's say if you mathematically, there's a big similarity. So anyway, the point that I want to make, if you cut it in building blocks like that, there are kind of generic building blocks that you will find over and over again in different modalities. And so for, I guess, signal processing people, this is very, practical, because somehow it allows us really to look at the thing as a bunch of modules. Okay. Now, I mean, so far I was in the continuum, but of course, if we go in a computer, somehow we have to discretize. And so the idea here, what we could do, okay, here we have a continuum, but we can write it as a sum of basis functions with some values in between. And maybe you can think of your basis function as just pixels. And so those would be the values of the pixels. And now if you take your physics that, okay, you need to master, so you know those new functions here, so that so this is really the effect of the physics, doing a kind of inner product with your unknown density map here, and unfortunately you have some additive noise, or not necessarily additive, but you have noise, measurement noise, and so that gives you really like a forward imaging model, because this is a good modelization of actually what you are measuring. And here, M, the index M here is really corresponds to the nth measurement or the nth detector. And now, okay, so that's the physics, but what you would like to do image reconstruction, you want to sort of rewrite that in terms of linear algebra. Okay, this guy here is finite dimensional, so you can write your vector Y. And now you could say, yeah, this vector Y of measurement would be a noise-free measurement that you don't know, plus noise. And now your object here is in the continuum, but I just told you I expressed it as a sum of basis function. And now if you take those S, which are the coefficient in those basis function, I can write a vector here that would be the representation of the signal S. And then I have the effect of the physics that can be encapsulated in this matrix H. That's the so-called system matrix. And now how do you compute it in practice? In fact, if you just use the linearity of the model, just insert this linear expansion, use the linearity of the integral. So at the end, actually, what you find that the MK entry of that matrix here would just be the inner product between actually this point spread function and the basis function. And now, if you have to solve a concrete imaging problem, you will have to study the physics and first see how actually you can compute this system matrix H. And once you have done this discretization, in some sense now you are in the discrete domain, you are ready to do an algorithm. Okay, example of basis functions. I guess in my lab, we do a lot of splines. And so splines usually are sort of translations of a generator that's called, let's say, the B-spline. And usually also for simplicity, the basis function we like to take separable. So there would just be a product of basis function along the different dimensions. So if you, very simple discretization would just be using a rectangle, but that's maybe a little too easy. Another one is maybe take piecewise linear interpolation. And so here's a convolution of the rect with itself. So that's a triangle that you could use here. Or let's say if you have a hardcore signal processing person, you could also eventually use the sink. Okay, so that would go with a Shannon type of representation. Okay, so now we essentially have the building blocks. Now, I think the operator, the physics, now I have to tell you how are we going to reconstruct our images. And again, you know, my sort of analogy, you know, clockwork, you know, like kind of classical stuff, okay? So discretized forward models. So I just more or less describe to you that, you know, most imaging systems, at the end of the day, once you've written down your equation, then your discretization work, you can write it in this form. So you're measuring y, and of course the problem is to recover the s, which is unknown. The difficulty being maybe that you don't have so many measurements, y, and you also have additive noise here. Okay, so here I'll go relatively fast, but let's say here the tools for devising classical algorithms. Usually they're based on some optimization, and so you have to refresh a little yourself with vector calculus. And so here we're just talking of a functional. So it's a map, you know, that goes, let's say, takes a vector and gives you out a real number. And now, if we want to minimize something like that, usually we'll have to look at you know, the gradient, and we have to do the differentiation of this thing to optimize with respect to, let's say, this vector of parameters. And this defines just the gradient, where actually you take the vector of partial derivatives. And now, if you are in an unconstrained optimization problem, you know that, yeah, I mean, the optimal is achieved. I mean, that's a necessary condition is that your gradient of the cost function be 0. And now, okay, so that's just the very basic stuff in optimization. And now here are a few useful identities, because now if this guy is linear, and in fact, if it's just a scalar product, I mean, so here you have, it's like, it's just the vector expansion, generalization of derivative of ax equal a. Okay, so that works also with vectors. If you have a quadratic form here with a matrix, if you differentiate with respect to v, you get this. And this one is very useful. So this, if A, for example, is a symmetric matrix, if you take the derivative with respect to v, you get this. And this is like optimization of quadratic forms. Okay, so very basic reconstruction. So that would be the least square solution. That's really if you were starting from nothing, okay? Like, let's say 60, 70 years ago. Okay, so you work to get your formulation here. And so that's your imaging system. And now what you would like to do is you would like to reconstruct some image, and I call that S tilde, such that, okay, now if you take your reconstructed image, you simulate on it the imaging, you get some simulated measurements, H S tilde, and you would like your simulated measurements to be close to the true ones. And that's what I'm writing here, okay, least square criterion. So then I can just say, okay, I want now as an algorithm, I want just to minimize this error so that my reconstruction is as consistent as possible with the unknown. Okay, so if you just now write your cost function like that, this is quadratic thing, I can just expand that using just, you know, very basic stuff in you know, manipulation of vectors and matrices. So I can write it in this form here. And here I have a quadratic function in terms of S, and here I have a linear function in terms of S. And I just showed you how to take this kind of derivatives here. So if I take the gradient, I get this. So that's very, very standard in imaging. Okay, and I have to equate the gradient to 0. And if I equate that to 0 and I solve it, I find that the least square solution is actually this. Okay, and this is like the pseudo inverse. Okay. And actually, at the beginning of my talk, I was telling you of the Poorman's solution. Actually, the Poorman's solution is called the back projection, which is just doing the transpose of the system matrix H. So it's sort of doing the reverse of the acquisition. But then there's this correction here that involves the computation of this inverse. And I mean, this works well if you have many measurements, let's say, at least as many measurements as unknown. And this is really the very, very basic thing that you could do. It's sort of, and now if you're lucky, like also the way MRI scanners were designed, and even they're still used like in hospital, if you go to have an MRI scan, in fact, the MRI is constructed in such a way that it's really actually measuring exactly your 2D transform, your 2D or 3D Fourier transform on the grid. And then, in fact, the H transpose, because you're dealing with the Fourier matrix, is actually just equivalent to the inverse. Maybe here there would be a complex conjugate if you are talking about Fourier. And so then it's super easy. Okay, but basic limitation, I mean, it's nice to write that, you know, going to MATLAB and doing this kind of inverse. If you see the size of those matrices, like, for example, well, MRI is easy to invert, but let's say 3D deconvolution, if you would have a cube of size of 512, okay, 512 cube, that's the dimension of S. So this matrix here would be 512 to the power 6. So it's not a computer large enough to even store it. So that's completely hopeless to write it like that and try to do a direct inverse. But of course, there are tricks using the Fourier transform. Now, linear inverse problems. Now, and that in some sense is the 20th century theory. So dealing with ill-posed problems. Now, usually we're not in the case, you know, where things are so easy that we can just take this least square solution. And because maybe there's a node space of your operator, and then you have to be a little careful. And then the idea here is to introduce regularization. And regularization so goes by the name of Tikhonov, so a famous Russian mathematician. And his idea was relatively simple. He says, okay, let's define some kind of function of goodness of our solution. And so let's take some operator L, apply it to our reconstruction. And to make it concrete, L could be a gradient. And okay, now we say, okay, we want to reconstruct our image. And I told you before, it's good to try to find a solution that's consistent, but maybe not too close because there's noise. Okay, so consistent within the noise. Okay, then there is still like infinite number of solutions that can, you know, satisfy this constraint. And then, you know, like to disambiguate here, you just say, okay, among all the possible solutions, I will choose the one that has the minimum of this kind of penalty here. And for example, here, if it was the gradient, so we'd say, oh yeah, I want to take an image that's smooth, let's say such that the energy of its gradient is small. So among all solutions, I want to take the nicest in the sense that it's the smoothest. Now, if you rewrite that using Lagrange multipliers, okay, and then you have, this is very, very standard. So it's like the variational form of those problems. Like here, you have the data term and the regularization. And then you can actually use your, you know, vector calculus. And by taking derivatives, you can crank out the solution, at least formally. And it almost looks like the least square before. The only new thing now, that instead of taking this inverse, which is not always well defined, we're adding here some term here, which actually makes this inverse well defined. And now the main point is that this solution is linear, okay? And it depends on lambda, which is our so-called regularization parameter. And I mean this, okay, it looks very, very basic, but I have to tell you, this is often the algorithm that is in sort of commercial scanners in one form or another. Of course, not implemented in MATLAB like that. I mean, there are tricks to implement that very fast. But for example, now, if we call this back projection, now if this red stuff here, which is a linear operator, we call it filtered, I mean, this is actually the filtered back projection algorithm. So it's not only valid for CT, X-ray tomography is actually valid for any type of imaging. I mean, this would be, I guess, your baseline technique of reconstruction. And I'm telling you, it goes with the 20th century. I mean, this is not the only way of looking at the problem. Of course, in the 20th century, I mean, people were relatively sophisticated. I mean, there's elegant theory, but then there's a complete different point of view. And this is the point of view of Wiener. And the point of view here is of making statistical models. Okay, so we're saying, okay, now instead of like Tikhonov kind of cooking up a measure of how good our image is, let's rather make some assumption about our class of signals. And of course, if it goes with Wiener, you know, Wiener liked a lot of Gaussian stuff. So you say, okay, the signal here is a Gaussian process, maybe with zero mean, but you know that Gaussian statistics or Gaussian processes are completely characterized by the covariance. So we know the covariance. Now, if it's a stationary process, that would mean, oh, we know the spectrum. I mean, in the statistical sense, we know the spectral shape of the signal we want to reconstruct. You know, over all the family of possible signals we want to reconstruct. And then actually you can formulate the Wiener solution, and that's quite elegant, because with the Wiener solution, you can really try to reconstruct the minimum mean square error solution. And so that's the best possible solution that you can come up with to reconstruct your signal. And this will even be as good as better than even the best neural network, okay? If this hypothesis is satisfied, because it's the global optimum, you cannot do better. But now there's also something very nice with Wiener theory, is actually you can also formulate it as a maximum a posteriori estimator. And for Gaussian, this is completely equivalent. And then you can write it like that. And actually, I think this way here is very enlightening, because you see it has like what's called a data term. So here you're trying to reconstruct something that is close to your measurements. So it's consistent. And then you have a sort of statistical term here that gives your prior information that is statistical, and that involves here the covariance. And actually here it's the square root inverse of the covariance. And now now, okay, you have like two points of view. Either you're a statistics person, or let's say you're a determinist person like Tikhonov. But actually, if you look at the Gaussian case, I mean, they're equivalent, because this was the Tikhonov solution, okay? Here, same quadratic term here. Here we had like, let's say the prior statistical term here. In Tikhonov, he put this energy of, let's say, the gradient of S. And now, in fact, if you interpret the L here, so it's the operator of Tikhonov, if you say it's the square root inverse of the covariance, then you see actually that the best regularization is the whitening operator. Okay, so if you know something about your process, about the statistics, then you can actually say that the optimal prior information that you can give, okay, is the one that will sort of create the flat spectrum. Okay, so that's the whitening filter. And that's completely optimal. And you see then that's completely optimal. Okay, now you can ask yourself, okay, how are we going to reconstruct in this 20th century world? And I mean, either if you're Tikhonov or Wiener, we've seen their equivalents, so you can write a cost function. Actually, the one of Tikhonov, I showed it before. And then you will run the steepest descent algorithm. I mean, this is the sort of, you know, most basic algorithm that you can do. It's actually interesting that now with neural networks, I mean, people were having more or less sophisticated algorithms. Now, when we're with neural networks, we're back also to steepest descent. Okay, so anyway, okay, here's like the Tikhonov form of the criterion. You take your gradient, And that's important when you do optimization. Always take the gradient. And now the steepest descent. What you will just do here, the algorithm. You will modify the current estimate. By like evaluating the gradient here and sort of correcting by the gradient. Of course, when you have converged, the gradient is 0 and it doesn't move anymore. Now, if you write it iteratively like that, rather than doing MATLAB or direct reconstruction, there's an advantage because, for example, you can impose also positivity constraints by, as you go on. Oops, sorry. As you go on here, you can impose that the reconstruction is positive. Now, let me show you a little how this works. I mean, this is super basic in some sense, but it shows you interesting things. Now, here is actually what happened. Here is an image that is blurred with additive noise. And now, let's just take the least square solution and just do a gradient descent based on the gradient of the least square. And in fact, this was the first deconvolution algorithm that people proposed. And it's also very similar to the Richardson-Lucy that's used in astronomy. And it's called like a Van Sittert algorithm. So let us just iterate. Okay, so we're just iterating. And you see the image gets kind of sharper. But as you let it iterate, I mean, it's trying to fit the noise, and actually it becomes really terrible at the end. And actually what early researchers or practitioners in imaging would do, they would just let it iterate, let's say, 30 times and stop, and that would be the deconvolution. But of course, to signal processing people like us, that's not very satisfactory. Actually, if you let it iterate to infinite, you get complete crap because it's just fitting the noise. So then you do more like a la Wiener or Tikhonov, if you introduce this regularization constraint, and then now you have a factor here that is lambda, you're putting more or less strength to the regularization. And then, I mean, you can more or less run the same iterative algorithm, but with a correction that takes into account the regularization. And then it depends now on the regularization parameter. So if you don't regularize enough, you get like least square, lots of noise. If you regularize too much, you get something blurry. And so there's a kind of optimal setting here. Of course, this is not super good. It's, like sort of very classical approaches. And now, what about the regularization operator? What are people using in practice? Actually, in practice, they're very much using the gradient or the Laplacian. Now, for example, the Laplacian operator is actually gradient transpose gradient. In the frequency domain, it has omega square. The gradient, if you look at the modulus, you could look at it a little at some kind of square root of the Laplacian. And you can also have like fractional Laplacian. So it would be omega to some power gamma. And actually, if you put this kind of models or operators, this goes very well, actually, with kind of fractal models. Let me see here, because if you have like a fractional Brownian motion type of models, and in fact, those were defined by Mandelbrot, but those are those that are exactly whitened by, sort of fractional iterative of the Laplacian. So concretely, that what this means, essentially, it has a 1 over omega gamma spectral decay. Now, if you look at biomedical imaging to a first approximation, if you look at the spectra, I mean, it is actually very well satisfied that the frequency content goes down with this kind of power law. And so this can be really some justification for why people are using, for example, a gradient and Laplacian for regularization. In fact, you can also give a kind of fractal or physiological point of view because, lots of imaging For example, functional imaging will measure, for example, oxygen concentration of the blood. And if you look at the blood, arterial trees, I mean, they're very, very much fractal-like. If you look at bone, it's also very fractal-like. So, for example, that's mammogram. So physiology has many kind of self-similar structures. As for example, this is a brain. So the arteries in the brain. And so that can also be like a good justification for this kind of regularization, which is actually used in practice. Anyway, so at the end of the day, let's say if you were sort of going with the philosophy of 20th century, if you want to do an algorithm, so you need to determine H. I think H transpose is important too. And then this is the formal solution. Okay, it's a one-step thing, but of course you cannot compute that because it's too large matrix. So what you do is a steepest descent type algorithm. And now what's important is this A here, which is called the normal matrix. So it really depends on the physics. And this guy here depends on the regularization. And now when do you get fast algorithms? So you get fast algorithms when this is fast. Okay, this I told you is like a gradient. So this is a convolution. So L transpose is a convolution. And now in the particular cases where A is also a convolution, then you get a fast algorithm. And now what's really nice, actually, that most of the modalities that I've described to you, the A here, which is the HH transpose, for example, for the convolution, it is clear this is a convolution. Okay, so you can do that with 2 FFTs. So it's fast. Now, even with tomography, I mean, if you do the Radon transform or transpose of Radon transform followed by the Radon transform, remarkably, this then is equivalent to a convolution. So you don't even need to compute the Radon transforms anymore. And MRI, even if you do sampling in Fourier, followed by transpose of sampling in Fourier, remarkably, you can write that down as a convolution. So actually, all those guys can be implemented quite fast as convolutions. Okay, so this gets me here. So we'll stop at that point, and we will take questions. And then I'll meet you again for sparsity-based image reconstruction and also learning-based approaches. Oh, okay, so now we are hitting part 3, sparsity-based reconstruction. You see some kind of sparse watch mechanism. And so that's what I will specify as second generation in our story. So linear inverse problems now comes in sparsity. And, in a cartoonish way, so as I was talking about the 20th century, so 20 goes nicely with 2. And so one was using like L2 norms, and 21st century people at the beginning of the 21st century then switched to L1 norms. And so, like if you look at the evolution to norm P L1. So why did people promote the use of L1 norm? So the first reason was because of the wavelet transform. Because, for example, if you look at images of, let's say, wavelet transform of biomedical images, if you go in the wavelet domain, and so here, everything that's gray here represents 0 coefficients, okay? So that's what if you go in the wavelet domain, so you have relatively few significant coefficients, and so that's called essentially that the wavelet representation is sparse. And it is known in mathematics that if you minimize L1 norm, that you tend to promote solutions that are sparse, so that have a few significant coefficient, but that the majority of coefficient is close to 0. And so that works with wavelets, but there's earlier work by Rudin and Osher, very famous, that where actually they used the fact that the gradient should be sparse. And if you measure the L1 norm of the gradient, that's called a total variation. And then also like the wavelet people, Mario Figueiredo, Ingrid Dobeschi, then presented algorithms where you can kind of reconstruct images by adding a penalty here so that the wavelet transform of those images should be sparse. And that also, the fact that wavelets are good ways to sparsify images is also because wavelets are good to compress images. When you compress, actually, you try to have a representation that has few significant coefficients. And then came the theory of compressed sampling by Donoho, Candes, etc. So that had a huge impact during the past decade. Now, sparsifying transforms, so what I said, images are well described by a few basis coefficients. And so this is even like an experiment we did like quite some years ago in the lab, where we were actually looking at MRI images and now keeping more or less coefficients. And so if you keep more or less coefficients, of course you will have a degradation of the quality of the image. So here we are measuring the error. So if you have very few coefficients, you have a huge error, and as you take more and more coefficients, the error goes down. So anyway, when one compares all kinds of different transforms, like let's say Fourier globally, or DCT, or wavelets, one finds actually that the wavelets here, for a certain percentage of coefficients, tend to have the smallest error. And so that sort of justifies the use of a regularization functional that would be the L1 norm of the gradient. Now then came also the theory of compressed sensing. And so the theory of compressed sensing, once you have discretized our framework, so this fits very nicely in that theory because they also consider a linear inverse problem of that form, but usually it's written in discretized form, so where we always have our system matrix. Then we have a representation of the signal, S equal WX. So W here could be a wavelet transform, and X would be the expansion, the wavelet coefficients. And so when you say that the wavelet transform is sparse, so it means that the L0 norm, so that would be the L0 norm of the wavelet coefficients. So that will just count the number of guys who are non-zero. And so it should be a certain number K, but which is much smaller than the total dimension of the wavelet transform. So now when you combine, just substitute this WX for S here, then you get an equivalent system matrix that is H followed by W, which would be the sparsifying transformation. And then once you've written it like that, you could specify the reconstruction problem, like producing something that is consistent. So you try to minimize the error between the measurements and the simulated measurement, subject to a constraint here that the number of significant, let's say, wavelet coefficient be small. And now, okay, so minimizing L0 norm, so that's essentially NP complete, NP hard. So there is actually a proxy which is using the L1 norm. And so people, Donoho, Candes, Tao, have shown that if the matrix now satisfies certain properties that are called restricted isometry or robust null space property, then in fact, if you minimize, solve this problem here, so which is essentially like trying to minimize this data fidelity loss subject to the constraint that your L1 norm should be smaller than some bound that you have, that if you minimize that problem, actually you can find the solution of the L0 problem. And in fact, this can also be represented like that. It's often represented with this colorful sort of composition of system matrix and sparsifying transform. And so in compressed sensing, you say, yeah, you're measuring relatively few measurements, and you have a signal that lies in a higher dimensional space. But what you know, that actually the signal has only a few active coefficients. Of course, you don't know which ones are active, but you know there are few. And in that case, actually, you can also reformulate maybe the problem in this way, which is closer to what we saw like in the 20th century. So we are having here a consistency criterion. So you're trying to reconstruct the signal that is close to the data, and you're minimizing here the L1 norm, to sort of disambiguate all those infinite possible solutions that would satisfy that. You choose the one that has the smallest L1 norm, and hopefully this is the sparsest also. Okay, so let's try to understand why L1 is better than L2. Because you could say, yeah, in the 20th century, they were focused on 2, then they went with 1. So what's the big deal? And therefore, it's actually nice to revisit a little this least square estimator that we saw before. So if we look at it at the level of one component, so that's one measurement. So once you have discretized, you can also say that one measurement can be obtained by inner product with your signal X. Now that's the unknown, plus noise. And so you have a system matrix. And now if let's say we were doing like L2 regularization. So the prototypical way of stating this would be like that. So you just don't put a L operator here, it's just identity. Okay, so you're trying to solve that problem. Now we know that the solution is that I showed you before. And now what is interesting here, maybe this is not as well known, but because actually this formula, so that's the standard least square formula, but in fact what you can do, you can write it in this form, which is maybe more interesting theoretically. You can say that the least square solution is actually a linear combination, okay, M, here we have M measurements, a linear combination of, in fact, the H's, and the H's are actually the analysis function. So those are the vectors that actually define the discretization of your problem. So this is sort of weird. It just says that the least square solution lies in the subspace that is spanned by the measurement operator, okay? And actually the A is given by this formula there. So it's not exactly the same. In fact, what happened here, we have commuted the application. You see this formula here, it's equal to this, where we have the filtered back, the back projection first, the filtering after, and it can be shown that actually you can do the filtering first, followed by the back projection. Okay, so those two are equivalent, and therefore you can really interpret your solution as lying in the space spanned by the measurements. So that's what's written here. Now, generalization, constrained L2. Okay, now we can maybe here go to infinite dimension, but let's say if here you were looking at even something that lives in a larger domain, and here we have, but we still have a finite set of measurements here that are specified by those H1 to HM, and now we are specifying here a convex set of feasibility. And so this is somehow to specify, for example, the solutions that are consistent. So the solutions that are consistent, so those would be measurements that are close enough. Well, I mean, this is the true measurements, and those would be like simulated ones that are close enough, so the Z being close enough to the Y, that would specify a convex set. So now here's a theorem. So it's a representative theorem for constraint L2 optimization. So if this is a consistency constraint, so you try to be consistent with your measurement and you're minimizing the L2 norm. And then you can show that actually this problem here has a unique solution that's exactly in the form that I said before, that is actually a linear combination of the H's. And now this is very general because this can be an arbitrary convex set. So it means it's not only for least square optimization, it can be for any convex data fidelity term. But if the regularization is L2, it means that the solution will always lie in the space that's spanned by the measurements. And actually this is quite a limitation. And in fact, this will explain to us why you have artifacts in L2 methods when you have a small number of measurements. So now, if you look at L1, you can really look at the L1 counterpart of the same problem. So now again, we are like, let's say even living in a sequence space, but here can be infinite. And here we're just taking a finite number of measurements, okay, by doing inner products. And we have again a consistency set here that's, can also translate in the convex data term. And there we have exactly the counterpart of the previous one. So if you are trying now to produce consistent reconstruction subject to the condition that you're minimizing the L1 norm, so what does the theorem says? It says, well, okay, there's a solution set that is convex, weak star compact, so probably you don't know what this really means, but just bear with me, with extreme points of the form like this. Okay, so what is special here? It says, first of all, the solution is not unique. It's convex, so it's a convex set. Now, convex sets have something that's called extreme points, and you can think of a little like the corners of a convex set, like of a polytope. And actually, this convex set will be the convex hull of those extreme points. And now what the theorem says that all the guys that are at the boundary of the solution set and that are extreme points are sparse. In what sense? That they must be a linear combination of Kronecker, so that's like impulses that are located at certain positions. But of course, you don't know which positions, okay? But it says that, in fact, there are less guys than you had measurements. So essentially, this means that, the sparse solution, I mean, the solution, the extreme points of the solution of that problem are sparse. Okay, so if here you could put any convex cost, but okay, that looks a little abstract, but let me show you a picture. Okay, now if the conditions of compressed sensing are satisfied, then we know the solution is unique. And then this theorem actually shows that the solution is sparse, okay? But I mean, this theorem works also when the conditions of compressed sensing are not satisfied. So they're like still sparse solutions of the optimization problem. Now, if you crank up the lambda, okay, put more weight on the regularization. I mean, here you can measure the sparsity and here like increasing lambda and looking at different, measurements. Actually, that's just some experiment by showing that if you crank up the lambda, you will actually produce sparser solutions. Now, let us try to visualize that graphically because it is very, very enlightening. So the L2, so that's a 20th century problem reads like that. And we, in the constraint version, we can also say like that. So we have the consistency condition here, and we're trying to minimize L2 norm. Now, if you are in the 21st century, a compressed sensing person, you want to minimize the L1 norm, like here. Now, what's the difference? Okay, the difference now is, okay, let's look at what happens now if X lies in 2 dimensions. Now, if we want to do compressed sensing in 2 dimensions, we just take one measurement. Okay, now the measurement is this vector H1. It lies in 1 dimension, and you get the value. Okay, now you have your consistency criterion. So now you want to reconstruct something that is in a slab here of width 2 sigma. Okay, because you're just on this axis, so you're in 2D. This is the gray here are all the locus that satisfy your consistency condition here. And now you want to look at the regularization. Now you know that the L2 norm, okay, of a vector here. I mean, it corresponds to the distance from the origin, and actually all the points here on this blue circle are at equal distance from the origin. So essentially, to solve that problem, you blow up the blue circle until it hits your feasibility region. And I think this is just geometry. If you blow up the circle, it will intersect at that point, and it's exactly on that straight line. And so it means actually the solution will be in the space that's spanned by the H. In fact, this is exactly what the theorem was saying here. Okay, you are in the space spanned by the H. Okay, so that's, you can see it geometrically here. Now what happens with the L1 ball? So the L1 ball is this polytope. And okay, there again, you can inflate until it touches. And so now it will touch on this point here. And you see this point is sparse. Okay, that's what the theorem is saying. And maybe compressed sensing people will show you that picture and they will say, yeah, the solution is sparse. But remember, our theorem said the solution is not always unique. Can you guess the configuration where it's not unique? Look at this. Okay. Now, in this scenario, I mean, it's for a different set of measurements here, okay? I mean, a different measurement vector here. So now, actually, the L1 ball will touch on all those points here. So all those guys have possible solutions, including this guy in this particular case, but only those two are sparse. And actually, those are exactly the extreme points of the convex set. So that was what was, you know, extreme points of this form here. So that's what is emphasized by this. So now what's the relevance of this? Now the relevance of this, think of tomography. Okay, if you have few angles, now you remember that the analysis function are those long Diracs. Okay, so they look like, you know, the things along which you are integrating. Now, if you have few measurements, this H vector will be like some kind of long guys like that. And the solution must live in the sum of a few long guys. And so that actually explains where there are all these streaking artifacts that one often sees in tomography if you're trying to reconstruct using L2 criterion. And so if you have few measurement, L2 is very bad. And at least L1 here will give you a solution that actually does not depend on the geometry. I mean, they're just sparse points, okay? So you can really impose sparsity and actually this is not dependent on the fact that you're in the MRI or in the X-ray machine. Okay, so this is one way to look at reconstruction, I think, second generation method, which you know would be the counterpart of Tikhonov, but now I just told you that we switched to L1 norm rather than L1 norms. But now there was also this other way in the 20th century where we're looking at them from the point of view of Wiener, from a statistical point of view. And that's what I'd like to introduce to view now. Now there's a variational map formulation of inverse problem. And so that is more like the Wiener point of view. Okay, so we have again, like, let's say, an unknown density, your linear model H, you have noise. The problem is to reconstruct S given those noisy measurements. Now we have seen, in the 20th century, we write it like that with a 2 here, and that can be either Wiener or Tikhonov. And now for compressed sensing people, we put P equal 1. Okay, so that's one way to look at the problem. But now if we're statistics people, take a statistical point of view, we could replace, you know, this sort of norm regularization, but actually the log of the prior probability of S. So it's the prior likelihood. So taking a Bayesian approach. And so that's what I want to show you here. Okay, discretization of reconstruction problem I already told you about. So now what we would also need is a statistical model of the signal. And there actually, this is something we pursued some years ago. And this is what I call the theory of sparse stochastic process. So there's a book, if you're interested, it's even available on the web. And so we try to formulate this innovation model à la Wiener, but actually for non-Gaussian processes. And essentially, so Wiener says that, yeah, you have a process, if you apply L, you get some white noise. And then actually S, you could just reconstruct by doing L-1 W symbolically, with this W being a Gaussian noise. Now, what's not at all obvious here, but in this book here, actually we define noises that are not Gaussian, that are called the Levy noises. But essentially, otherwise, I mean, this kind of stochastic differential model can still be valid. So, I mean, even if the noise is not Gaussian, you can whiten it, and so you still have that kind of definition. And so this is really something that's defined in the continuous model, and also like has a link with Levy process. Now, if you have the stochastic model, now by using this kind of discretization of the signal that I was proposing before, we can actually discretize the statistics. Okay, so we can say, yeah, if we take our signal, we apply the decoupling operator L, we get white noise. Now, if we go in the discrete domain, we can take the discrete version of L, so it's a matrix L, and then we get something that's called U, and U we call the innovation. So it's sort of the decoupled version of the signal. And then actually this theory tells you that now the distribution of this U cannot be anything. It can actually only be part of the family of infinite divisible laws. And so those are very interesting because they're either Gaussian or have very, very heavy tails. Okay, so now here we have discretized the statistics. That's the new part. Otherwise, we can discretize the image formation, so that I already showed you. And now we are ready actually to write a probabilistic version of the reconstruction problem. And so here we are just using Bayes' rule, very standard in signal processing. So S is the signal, Y are the measurements. So what we want really, so that's sort of the important part, is the probability of the signal given the measurements. Now by Bayes' rule, we know that, you know, it's the probability of the measurements given the signal multiplied by the probability of the signal divided by the probability of Y, the measurements. Now, the probability of Y given the signal, actually, this is the probability of the noise, okay? Because Y minus HS, this is exactly the noise, so we know it. And now we just need to specify the probability of the signal. Okay, and the PY is just the normalization factor. So we can write all this like that. Now, if we say that now we have a transformation L that we apply to the signal that's able to decouple the signal by doing this innovation, then we know that our probability of the signal is actually proportional to the probability of the innovation because they are related by a linear transformation. And now I told you the U's, okay, maybe let me go back here. U is LS. And now my assumption here is the U's are independent, okay? Now the U's are independent, so U's is LS. So I can write the U's as a product of the probabilities of the individual components, okay? And then, now if I say, okay, my noise is Gaussian, but I could put anything else, but just for, you know, to make an easy formulation, I say my noise is Gaussian. So I can write actually this likelihood, and I can say that my probability of the signal given the measurement, so there will be the noise term here, which is exponential of this. Okay, that's where here you have the data term, and here you will have the product of the probability of the U's, which is the decoupled version of the signal. And then take the log and maximize. Okay, and we're done. And so that's the next slide. Okay, once I take the log, or minus log, minus log and minimize. So if I take the log, this goes away, and this product here becomes a sum. Okay, okay, so that's what I'm obtaining here. So this is the Gaussian part. So now I switch to minimization by taking minus log, and here is the part that corresponds to the signal. And what is the phi? Actually, the phi is what we call potential function, and it's just the log of the probability of those decoupled version of the signals. Okay. Now, to make a link with Wiener, now Wiener was telling us the signal is Gaussian. Okay, so if you decouple it, this becomes a standardized Gaussian, independent. So you have your Gaussian thing. If you take the log, you get a 2 here. So that will be a 2 norm. Okay, so we're exactly back in the 20th century. Now, if this PU, for example, we put a Laplace distribution, and by the way, Laplace is exactly a part of the family of infinitely divisible laws, then actually what we get here is we get actually this absolute value. And the last here is the student's distribution. So this is a sort of very heavy-tailed guy that you know, has like tails that decay sort of algebraically. And now if you take this guy, you get a potential function which is more like a log. And so here you see that we have here, okay, a sort of standard optimization problem, but here instead of having L2, we can have L1. Okay, but here we can have other potential functions which are like that. Okay, and now how do we solve the problem? Okay, so the method here is a sort of divide and conquer, sort of, you know, like state simpler problems. And the simplest problem would be if it was a scalar problem, like a pointwise denoiser. So we would have a linear inverse problem where, in fact, we're just identity plus noise. Okay, so the data term is here. And here, if we put like this probabilistic thing with the potential function. And now if we minimize that thing, we would get some solution. But okay, now what we want to do, we want actually this minimization. So it's a scalar minimization. So if we, for every y, we get a u. Okay, so the minimization of that problem will actually produce a curve. So where here I have the y, and here's the u that comes out, which is the minimizer of this. And now, depending on the type of regularization, so if I put the L2 regularization, it's Wiener, so it's a linear solution. If it's L1, you get this thing, which is a soft threshold that people like a lot in compressed sensing. And now if you take this sort of student type potential function, in fact, you get actually something that you can show that mathematically it's sort of equivalent to LP relaxation for P going to 0. So this red guy here, which would be this curve here, it would be a little like the solution for LP norm with P being very small, okay? But now what's interesting is all those formulations here are contained in the stochastic form, like of this sparse stochastic process. Okay, anyway, at that point we want an algorithm. And there, this is the maximum a posteriori algorithm. And here we have an innovation model, U equal LS. We want to minimize that. And so if we write this auxiliary variable, we can also write it like this. And it's a very natural auxiliary variable. And then the trick is actually to use augmented Lagrangian. And so augmented Lagrangian, so we will like, you know, like create this auxiliary variable U, but try to force U to be equal to LS. That you can do by adding a term like that. And also if you add Lagrange multipliers. In fact, the official way to do it is called the augmented Lagrangian and goes with the very famous ADMM algorithm. So you rewrite your thing to minimize here by now considering an auxiliary variable U and a Lagrange multiplier lambda. Okay, so that's the original problem, but the U is now an auxiliary variable. So you want to force U to be equal to LS. So that you do here with the Lagrange multipliers, but you also do it here with this quadratic term that will pull U towards LS. And actually then you rewrite the thing like that. And now the ADMM algorithm is actually very simple, it's sequential optimization. So what you do, you first assume U and alpha are fixed, you calculate S by minimizing this guy. And then you fix S and U and you optimize alpha, or you have this very simple rule for updating alpha. And last, you say that, okay, U is fixed and alpha fixed, and you minimize S. And I mean, this in principle looks a little more complicated because before we just had to optimize for S, now we have to optimize for U and alpha. Now the good news, the really good news, if we look at that problem, so it's the first one. So if U is given and alpha is given, if we write down the problem, actually it reads like that. And now if you have some memory of what we said in the first generation, what you recognize that, in fact, this algorithm is, you know, the algorithm of the 20th century, okay? It's a linear solver, okay? So this guy, you can just shamelessly borrow a very fast algorithm that engineers have devised for doing conventional image reconstruction. And then, okay, this is trivial. And now this part here, this is really nice because you see you have a sum here. I mean, this is fixed here. Now we have a sum. And so the problem here, also with the two, it's completely decoupled. And so we can solve it pointwise and using the proximal operator. So we can exactly use the nonlinearities that I've shown you before. And now the idea here is, okay, you have a very generic class of algorithms where actually you can just engineer the nonlinearity, which is a, you know, a nonlinear mapping, and to obtain an algorithm that will actually optimize your cost function. And in some sense, it's the simplest algorithm you can think of because this is an algorithm of the 20th century. So it's a linear solver of the type I described the last hour. And this is just a pointwise nonlinearity. So you cannot think of simpler algorithm. And I mean, at that point, I will leave the floor to Paul, because now Paul will tell you about some practical application of that to deconvolution, and also will show you how we can use our library, like Global Bioim, in order to actually calculate those solutions.
Hello, thank you, Mikhail. My name is Pol del Aguila Pla, and I am a research staff scientist at the Center for Biomedical Imaging in Switzerland and a postdoc at the EPFL's Biomedical Imaging Group in Lausanne. Before anything else, I would like to welcome you to ICASSP 2020 in Barcelona, which is my hometown, and deeply regret you did not get to visit it. Let's all hope that the times improve and you can visit soon. So I will proceed to talk to you a bit about the practical details of working with second-generation methods, focusing on a running example of the convolution of a 3D wide field microscopy image. So the convolution in wide field microscopy is a especially interesting topic because it's a fully 3D deconvolution, in the sense that it's a 3D deconvolution in which the impulse response of the system is it extends through one of the axes very far. So it has significant lobes to consider in X and Y when you go up or down in Z away from the point of focus. So to understand a bit more this, basically you have to think that a microscope is a 3D system in which you have a little knob in which you regulate which Z basically is going to be in focus. So this space here is supposed to be the sample space where you put the things you want to image, and you calibrate the microscope or you turn the knob until the red plane is aligned with this hypothetical sample that we're trying to see here. If this sample is thin, then you're going to get a 2D effect that we're going to talk about later. But if not, you have to take into account that the PSF spreads through the different Zs. So for example, here you can see a cut in the blue plane. You see a cut of the point spread function or impulse response, and you see that it's wider than it was at the red plane, which was the focus plane. In contrast, if you want to see it vertically, which we have here, the 3D illustration, you have the yellow cut. So how this 3D point spread function is derived from the physics of the system that are basically characterized by this pupil function, which in an ideal case like this is simply a function that tells you which circle and with which radius is your microscope allowing light to pass. The interesting part here is that the PSF you derive basically from this pupil function, and also and there's this factor that makes the PSF spread as Z moves away from the focal plane. So without getting into more detail, when you have a thin specimen, when you have a sample that you want to visualize that is very thin in the Z domain, this leads to a 2D convolution model, which is much easier. Simply if you work from the expression above, the equivalent to the impulse response is what is known as the Airy disk or the Airy function, and it's basically this evaluation of the Bessel function, and it looks like so. So it's this profile. I guess most of you have seen this. If you look at the radial profile, you see that the lobes are substantially attenuated, but still it's very different to convolve by this than to convolve by its Gaussian approximation. So if you want to really get specific about the convolution, substituting one by the other, it may not be such a great idea. And the behavior of this function is heavily characterized, as I was saying, by the radius of the aperture and the focal length that you've set in the microscope. So if you look at it in the Fourier transform domain, so basically at the transfer function, you see that if you cut it radially as before, it sort of looks like a triangle. And the explanation of this is that in order to derive the transfer function of the PSF in this convolution, you have to think about the pupil function that we said before that tells you where light is allowed to pass, and this transfer function is going to be basically the autocorrelation of this pupil function. And if you look at it radially, basically this is the autocorrelation between two square pulses, so it's roughly a triangular. So obviously, since now it's 2D, it gets harder. And what ends up being characteristic about the whole system is the cutoff frequency of the transfer function, which is basically coming from a ratio between the radius of this aperture and how far the focal plane that you're focusing on is. So when you have a wide field microscope and you have thin specimens that are properly focused, you can use all the toolbox that we introduced for doing simply 2D deconvolution. So here it would look like so. So if you have the cutoff frequency under pi, and you can take sinc bases that are separable in each of the dimensions on a grid, and then the analysis function that we've seen that they are these 2D airy disks. But then because of this condition, then you have that the system matrix can be easily computed by taking the samples out of the 2D Poincare function. So basically, because the sinc is in frequency is a square, that it's wider than the response of the sinc, of the impulse response. So as a result, both H and L, if you choose a gradient, for example, for the regularization, are matrices that are diagonalized in the discrete Fourier transform domain, which means that you can basically implement the linear step of ADMM as in the Fourier domain, speeding up computations highly. So dummy examples for these that are not specific to wide field microscopy is they basically found these 3 different examples out there that each work better with the Gaussian Laplace or student estimator when you use the gradient TV-like regularization and with optimized parameters. So this goes to say basically that you'd have to adjust, ideally you'd have to adjust the shape of your prior to the kind of image you're observing. So if you're trying to recover patterns like so, you probably shouldn't use a prior that favors patterns like so. But let's go back to the 3D, the convolution of wide field microscopy. So in some cases, you know a priori that your sample is not thin, and you want to image it as a volume. So you want to really have the information of the volume. In this example, we actually have 3D plus color because this is a sample of a C. elegans embryo. And the purpose is to have a reconstruction of different fluorophores that have been paired to different parts of the embryo and reconstruct the whole 3D volume. Of course, this is not done from a single microscope image, but what you do is you keep turning the knob, you keep changing the Z, which is in focus, or moving the sample, which is equivalent, and taking different images on these 3 fluorophores. And of course, that will result in streaks around the boundaries in Z to look very, very blurred, because as we've seen, the impulse response is very, very broad as you go far away in Z. So the result we're going to obtain is going to be this. You see that it looks much more resolved, although it admittedly still has some things that may or may not be artifacts, as we'll discuss later. So the PSF, in order to solve this problem, because of course otherwise it's going to be blind deconvolution, you can obtain it from an analytical model that you can actually download some software we have available to generate this PSFs given the setup of the microscope. And the convolution we're going to perform in Global BioIm, which is our library, which, as you'll see, it's quite neat. So now, as I've spoke before, we're going to be concerning ourselves with practical problems of when you're implementing second-generation methods. So the first one here is that we've talked throughout the tutorial, we've talked about implementing convolutions in Fourier space. But for doing that, for example, with this very broad PSF in Z, actually, if you download the data later, which I will give you a script to download, you'll see that the PSF, the size of the PSF volume is the same as the size of the data. And that's because there are lobes that are relevant very up in the Z domain that we're scanning. So as the influence of the middle point on reaches the upper part of the sample. So it's a very extreme case. So in order to perform that convolution in Fourier, then we will need to pad the PSF array. Otherwise, we would get the result of a circular convolution, which is not what we want. We want to have the linear convolution between the PSF and our optimization variable in order to compare it to Y. So that means that in order to compare it to the data, we will need to extract the piece that is relevant of the result of our model prediction given the optimization variable, right? So that will mean that we will need a further operator here, which is a patch extraction or masking operator. So that sort of breaks what we've been talking about solving the linear step of the ADMM in Fourier, because this patch extraction or masking cannot be done in Fourier, or it would be a convolution in Fourier, which is sort of the point, right? Another practical issue is that usually, although we've talked about the theoretical principles of putting priors on variational problems through this map theoretical explanation, usually the TV that has been more successful in image reconstruction is the one that uses group sparse norms. So this is the L2, L1 norm across different dimensions in order to create group sparsity. So to consider the value of each gradient vector in a voxel as a group, and you want to sparsify that set of groups of gradients, right? Yeah, so L is the gradient as explained. And of course, this complicates a bit the issue. Yeah, you cannot think about it's not exactly the same formulation we've seen before as the sum in the number of samples of priors. So it changes a bit. And then there's the other thing, which is what we're recovering are fluorophore concentrations for each channel. So this, an important thing to say right now is that this problem is going to be run 3 times, one for every color channel. So it's also, yeah, so another practical consideration is we want to recover non-negative fluorophore concentration. So that you do in proximal optimization or these kind of second generation methods, you do by imposing a regularizer, which is basically an indicator function that puts infinite cost to some value in the volume not being non-negative, so being negative. So practical considerations, again, implementing proximal optimization is hard. So there are many things that you may want to do, like optimize memory management, implement different convergence criteria, have code that is portable to the GPU. So imagine that you're starting to prototype this and you take a smaller piece of the volume and you're trying to deal with it. And suddenly you realize it's taking long and you want to switch to GPU. So sometimes this may mean reprogramming or reformatting your code so that it works on GPU. Then there's also that every linear operator that you use, you've seen that the many pieces can serve for many imaging modalities. You want to make sure that each of them is implemented as efficiently as possible. So reusable code would be convenient. And then beforehand, you don't really know which one is the algorithm, the optimization algorithm that is going to work better. So we've talked about the ADMM because it's very interpretable and very convenient. But what if you want to try further? What if you want to try different splittings within ADMM so that they allow you different computational advantages or memory compromises? So this is the practical life of those working in this field, as you may well know. So what we developed is or what the group developed is a global Bioim, a unifying MATLAB library for imaging inverse problems. Please click the button to download. And this library is built on top of 3 abstract classes. What abstract classes mean is basically that it's definitions of what a linear operator, a cost function, or an optimization algorithm should be as an entity, and what they should always have. So these abstract classes then are by inheritance inheritance, you have you are able to define, or we've defined several linear operators like a convolution, gradient, Hessian, X-ray transform, different cost functions like L2 cost, L1 cost, the mixed norm to grade group sparsity effects, non-negative constraint. Then you have several optimization algorithms like ABMM, Chambol-Pock, gradient descent, or other primal dual splitting methods. And the important thing is that each of these objects, once you construct it with the basic parameters it requires, it has everything you need later, or everything the optimization algorithm will need in order to run. So operators are paired with efficient implementations of the forward, of the backwards, or of the adjoint, and of the adjoint and forward, which sometimes there are more efficient methods for doing both things consecutively than doing one and then the other. Then the norm of the operator, either a routine to estimate the norm or its known norm. Then each cost function has, whether it's differentiable or not, and in that case the gradient, whether it's convex, it's prox, the Lipschitz constant, etc. And then each of the optimization algorithms will harness all of these properties in order to run. So as a result, well, let's first look at how we would formulate, or one of the options that you can formulate to solve this problem with ABMM. So in this specific case, we choose 3 dummy variables, U1, U2, and U3. And basically you see that they correspond to what is evaluated in each of the terms of the cost function. And the benefit of that is that then the linear part of the optimization in ABMM, so when you solve for S in the augmented Lagrangian, that can be done in Fourier then. So in specific, the augmented Lagrangian looks like so. So basically you have the cost function utilizing U1, U2, and U3. And then for each of them, the Lagrange term and the relaxation term. So here actually is where you can see that if you want to solve for S, you'll have these terms here, and all of this can be done in Fourier. There's no S anymore. So to see how quickly it is to implement this solution in Global BioIM, I'll be reporting different extracts of the code. So first you define the operators. So H as the linear operator of convolution that works, basically you give it the FFT of the impulse response you wanted to implement. Then you have the gradient, which only needs to know which side is going to be the variable that it will receive. Then you have the identity, which we're going to use to pair with this dummy variable with U3. And then here there's one of the options that you can give to the code, which is to memorize the outputs of the operators, which depending on what you're using, it's more or less efficient. So basically what this does is that every time one of these operators is applied, its result is stored so that if it is called with the same input, it doesn't need to recompute the output, but it simply gives whatever it has stored in memory. So then the next step is to define the cost function. So this is quite easy, as you can see. So you define the L2 cost and you give it the dimension and the term of comparison Y, so the data. And of course, you'll need to compose this L2 cost function with S, right? The patch operator extraction. So we basically define the selector patch operator in which we give it the size of the variable and what it should keep. So which indexes it should keep in each dimension. You can look through the code later, which will be provided. And then basically you compose both by simply stating that the least squares cost is the composition or the product between these two objects. So whatever when you want to evaluate this function, the first thing, whatever you give it is going to be passed through S and then through the L2 cost. And then for the regularization, it's similar. You simply define the mixed norm regularization as a cost mix norm to 1. And basically you give it the size of the input. So this is going to be the variable size times 3 because the gradient has 3 directions. And and then you tell it across which index you want it to do the groups. So in this case, it's the fourth index because different components of the same gradient are going to be in the fourth dimension. So then you define the regularization parameter, lambda, and the non-negativity regularization is simply the cos non-negative, which we have as a template. And then to configure ADMM, we basically give it a list of linear operators and a list of cost functions, and they should be co-indexed. And basically we tell it, okay, age is paired with the least squares cost. So you're gonna pass things through the operator age and then apply the least squares cost that we've defined before, which included S. Then lambda TV times the mixed norm regularizer is gonna be paired with the operator L. So you're gonna first do L and then pass it through the mixed norm regularization to obtain a TV regularizer. And basically the non-negativity regularizer goes paired with the operator identity, which just forwards the optimization variable. So in ADMM, you have to select these penalty parameters, which we basically set empirically. And as far as here, you've already defined what ADMM has to do. So the only thing that you have left to do is basically tell it the maximum number of iterations, the convergence criteria. You have the option to include an output object here. So to tell it to run something every certain number of iterations. In this case, it just runs a line, it prints a line with the cost value, number of iterations, timings, etc. But this framework has the option to include many more things like plotting the current loss value, etc., etc. And then basically you're done. You can run your ADMM algorithm. So now I'd like you to see a bit the code, and this is basically the code file you're gonna get from us with this tutorial, 3 files. So one is to download the data so that you can experiment yourself. One is to download and install the global Biomedical library. And the third is simply the script that processes the data and runs the convolution. So you can see that it's about 120 lines. And what's interesting here is that the first 50 basically deal with data handling. So with loading the data from disk and reformatting for all the computations that have to be done later. But this could be heavily reduced if we change the format of the data. So basically what is relevant here is what I've shown you. So the operator definition, the cost function definition, the regularization, configuring ADMM and running it, and then storing the results. Okay, so basically it's a very fast way of prototyping, and I think it could help you out a lot in your research too. So basically, the final remark or feature that I want to exhibit about Global BioAIM is that if you use this function, use GPU, and ensure that all relevant variables are passed through this GPU to CPU converter, just by changing 0, 1, or 2 as a flag in the code to this function, you can do the computation in GPU or on CPU. So this is actually very, very convenient when you're prototyping. So to close, I'll basically want to show you the result of running this deconvolution in a more flashy way. So basically, here you have the data, and here you can observe the blur across the Z dimension, as we were saying before. And here you have the result of the deconvolution, in where you have to take into account that these green lines are not necessarily artifacts, but they can be dividing lines between different parts of the embryo. So thank you very much. Now I'll leave the floor again to Mikael, which will continue with second generation methods and then proceed on to third generation methods and learning. Thank you.
Okay, so welcome back, and thank you, Paul, for giving us this demo. Maybe I'll just like to emphasize here, there's the link to this Global BioIM library. And also, I mean, you can use it to try other modalities, for example, MRI, CT, etc. And there's also some paper that describes the use of the software. Now, maybe to end up on the subject of second generation methods, I'd like to tell you about one application in the lab, which is differential phase contrast tomography. So it's a kind of computer tomography that uses very pure X-rays. And this is done at the Paul Institute. So this is the Swiss light source. So a very expensive CT scanner that costs $1 billion Swiss francs. And now what we can do here is also actually not only measure absorption, but phase. And there's an interferometry setup that allows you somehow to measure also, get the phase information from those measurements, which are also projections. Now, the mathematical model is very similar to the one in computer tomography that uses the radon transform that we saw in the first part here, but it actually adds here the derivative. So then we can also like set up the linear forward model, which is as usual, but now it has a combination of X-ray transforms, so which are integral projections followed by a derivative. And then you can actually implement the whole setup. And now this was done by my former student, Masi Nilshan. And so he implemented more or less the ADMM counterpart of what Paul had presented for this phase contrast X-ray, and then obtained very good results, and actually results that compare very favorably with the conventional algorithm they were using, which is more like a first generation method, because they were like more physicists developing the instrumentation. And now what we tried here is to make reconstruction much fewer views, so 180 instead of 700. And we could actually, if we look here at magnification, so you see that this reconstruction using sparsity, priors, and TV is much better than what you would obtain using a conventional reconstruction. And now the interest of this is because usually they record like 700 and something views. And now we, by reducing the number of views here, like by 2, etc., so we could essentially maintain the quality up to almost like going down to 90 views. And the quality also of our second generation algorithm was consistently much better than the direct reconstruction, which obviously also makes sense because we're in this sort of compressed sensing regime. And so this improvement is quite significant for application, because imagine the cost of the Swiss light source. And so therefore there's a cost associated with making tomography measurements. If you can reduce the number of views optimistically by a factor 10, means you can have 10 more experiments and so do much more very high resolution image. Okay, so this is not only valid for like computer tomography, of course, compressed sensing. There are many applications in imaging, especially in magnetic resonance imaging, where the leading manufacturers actually have now created special sequences and also software that does compressed sensing and applies like total variation priors and to do very fast imaging. But there are many other imaging modality, interferometry, terahertz imaging, holography, coded aperture, spectral imaging, ultra-fast photography, where people have used this methodology that I just presented. So it's a compressed sensing methodology to do advanced imaging. Now, conceptual summary, maybe to finish up on the second generation methods. So we saw that we have always like a physical model. And now if you look at a sort of ADMM type algorithm, in fact, if you split the variables, you can sort of introduce here, some prior information that can either be statistical or in in the spirit of favoring sparsity. And now, you know, this is relatively stylized, but if you look at the ADMM type algorithm, what you are doing, you're essentially alternating between a linear step that's relatively classical because you can reuse fast algorithms from the 20th century or linear solvers. And then you have a nonlinear step, but for example, like with this ADMM algorithm, it can be at the pixel level, is completely decoupled. And so this can be like a nonlinear pointwise processing. And that we like to see as a statistical or denoising step. Now, the current status on compressed sensing type methods or sparsity promoting methods is that in general, we obtain higher reconstruction quality than the traditional approaches, and that has been used in many modalities, starting very dramatically with MRI, to the point that, in fact, in MRI L1 reconstruction, they call even compressed sensing. Faster imaging, reduced radiation exposure, that's the fact that you can get away with less measurements. And so that's very valuable for application and also clinical use because safety to the patient. The cost to, the price to pay here is increased complexity of the algorithm. But now if you use those ADMM or FISTA that we didn't really discuss, but here you're kind of alternating between linear and non-linear. And typically in about 70 iterations with like well-optimized algorithms, you can get a reconstruction. So as a rough estimate, you can say those algorithms will cost you maybe about 70 times more than the classical, but they do more sophisticated reconstruction. Now, outstanding research issues. Now we'd like to link those techniques with statistical modeling and learning, because now it's sort of more like model-based, and then so essentially what you'd like to do is to match the model to the application, and also continuous domain formulation. And so for those who are interested here, we have, in fact, a paper in CIBM review that revisits this reconstruction framework in the continuous domain, and actually shows that solutions are splines, which maybe you won't be so surprised if you know the kind of stuff that I like. Okay, so now we are finished with the second part, and please feel free to ask your questions. To ask your question, we'll just see you on the chat, and I'll be back in a few minutes. Okay, now let's move to the final part of the talk, and also of the title, which is the deep learning, I would say, evolution revolution. And so this is really the emergence of third generation methods. I think many of you may be very interested here. So the first thing we can do learning within the current paradigm. It's more or less what, you know, within the framework that Paul was presenting. Maybe what you could do, you could tune the parameters. And so there's the lambda to tune, this regularization parameter. You may also have to calibrate the model parameters. And those are kind of semi-blind methods, sequential optimization. But what you could also do is you have this idea of this decoupling operator, L. And I mean, this you could also learn it. And so this is related to dictionary learning methods. And so there was, I think, work like predating deep learning about learning dictionaries for image reconstruction, and that's also gives you some performance improvement. And then the other thing that you can also do eventually, remember there was a potential function, so you could learn the potential function, and using some kind of CNN type parametrization, backpropagation. And this is what a few researchers have done. And so this was sort of learning make its way in imaging. Now, if you go back to the structure of an iterative reconstruction algorithm of the type we discussed in the second generation, if you look at the ADMM algorithm, really what you have here is an alternation between a linear step and a denoising step. So the denoising, if for the algorithm I described, it's really pointwise. So it can be looked at the pointwise nonlinearity. So it's sort of similar to, let's say, a ReLU. Okay, but I mean, this is a soft threshold, so it's a pointwise nonlinearity. And this, I also told you conditions on H, where in fact the linear step was equivalent to a convolution. Okay, so this algorithm in fact has the structure of a deep convolutional neural network. So there's a convolution followed by pointwise nonlinearity. And I mean, the people, in fact, there was Lequin and others, and sort of saw this connection pretty early on. And then they had the idea of kind of unrolling unrolling more like an iterative shrinkage thresholding algorithm or ADMM algorithm. And then the idea was, okay, we unroll the thing, but now why don't we learn all those linear steps? Because this could be implemented by a neural network. And then by, in fact, learning those linear steps, then you're really like in the context of deep learning for doing imaging. And then there was the appearance of deep convolution networks for solving linear inverse problems and doing imaging. And so I must say I'm pretty lucky in my lab because I had a postdoc, so Kyung Jin, who came to me and he was insisting that he wanted to apply neural networks to computational imaging. Of course, we're more like principle-based people that were more like thinking like compressed sensing, but nevertheless, I let Kyung develop his software and to see what would happen. And so the problem that we chose was really to look at the compressed sensing problem. So trying to reconstruct images from a limited number of views. And so we could like train the network using the reconstruction, the high quality reconstruction, and somehow doing first filtered back projection reconstruction from much fewer views, which has artifacts, and then training the neural network to compensate for the artifacts. And so Kyung proposed to use the UNet with skip connection. So it's a very popular neural network that was used for segmentation, and tried to use that for doing computed tomography. Of course, he was not the only one, but we were among the very first. And so here are the results. Okay, so this is a CT data. So it's like data from the Mayo Clinic. So here's the ground truth. So ground truth reconstructed from, let's say, more than 500 views. No, well, 7 times 140. Okay, so this is like what we're using as ground truth. Then we are doing here a filtered back projection reconstruction from much fewer views, which has all kinds of artifacts here. And then in principle, this would be like the conventional method working with this. Then we can, on this restricted number of views, we can use the kind of methodology that I described to you just before, using total variation. And you get, like in this case, a close to 5 dB improvement. And that was like the result of researching compressed sensing. Now, what you can do now, and what Kyung did on other images, but in that framework, he actually trained a neural network as a regressor that would take this as input and try to output this. Okay, and then, of course, we apply it here to this image that the neural network never saw, and here's what we get. And this was rather astounding, because now suddenly with a neural network, we get another 5 dB improvement. And it's almost as much, you know, the first time one tries that as the gain that was obtained from 10 years of research in compressed sensing. So that was, you know, very dramatic. And I mean, then we could publish the paper. And so it was one of the early papers published on neural network applied to Biomedical Image Reconstruction. Actually, this paper has become really popular. Actually, so popular, it's pretty well known. And in fact, I'm very happy here to report that we are actually getting the 2019 Best Paper Award, in fact, at ICASSP, okay, which unfortunately we cannot attend physically, but that's a recognition for this work, which attracted lots of attention. I must say we were not the only one, but in some sense we were lucky because we could publish relatively rapidly, and I think it was a very solid paper. And I mean, here's some other examples. So, you know, so this is some other image going even further, like reducing by 20. So that's super extreme. If you tried filter back projection, I mean, the kind of linear algorithm, get all kinds of artifacts. With total variation, I mean, you can reconstruct, but I mean, you really get something cartoonish, like very piecewise constant, which you would expect from total variation. And now if you do with the neural network, you get much better results, okay? And so that was with the microcity data. In fact, this data from the Swiss light source. And it works as well. So here, I mean, we're like operating in a much higher noise regime, less contrast, so filtered back projection full of artifacts. Here we're reducing by 14, so it's much more than what I was presenting you before, so with TV, it kind of works, but I mean, if you compare to the ground truth here, you're washing out details. And the neural network, of course, it also loses some structures, but does a better job. And so we get also like a better signal to noise ratio. Okay, so CNN, this looks really super promising. So what are the conditions for utilization? Now it's really, we need to be in a regression setting. So neural networks for developed for example, for classification or doing image processing, they work well if you have an image as an input and an image as an output. And that's the reason why we like to do this filtered back projection first. So it's, let's say, an old style, not so good reconstruction with artifacts, and then train actually the neural network to take this image to produce another image. And so this would be a mapping that goes from an image into another image. Now, there's a fundamental change of paradigm here because you need now extensive sets of representative training data. And in fact, your algorithm will only be as good as your data, together with gold standards. And having the gold standards in medical imaging is not so easy because it's a sort of circular thing. And because you never know what's the real thing. And therefore, actually, what works well is this compressed sensing, because we can have a gold standard that would be a high, reconstruction using many views, and then we can train the neural network to go from few views to, trying to be as good as a reconstruction with many views. Now, the application niche, there are many. Denoising, so also historically denoising, super resolution, data extrapolation, so that's very useful, for example, in biological microscopy. Reconstruction from fewer measurements, so that's what I just said. So it's trained on high quality full view data sets. And the other thing that works too is, because if you have, let's say, a conventional algorithm, super sophisticated, but it's slow, so maybe there you could train a neural network to emulate your slow algorithm, because neural network, I mean, what's slow with neural network is to train the network, but once it's trained, it's super fast. And so that's also an issue. Now, design of convolution neural networks. So general principles, what do we need to take care of? So there's data preparation. And there I would say data preparation, it's good to use your classical linear reconstruction algorithm, because this maps the data back into the image domain. And then, as I said before, just use the CNN to correct for the artifacts of first generation methods. Okay, so this is a connection with first generation methods. Somehow here we skipped all the development that we told you about, all this nice thing with, you know, iterative ADMM. And in fact, now the people who came, started using neural networks, let's say after the feed forward, like what Young was doing, what was proposed. In fact, they made a connection with second generation methods. And I mean, the first thing was that just unrolling to justify the deep architecture. But what is even better is what I call hybrid methods, and that's also goes under the name of plug and play. Because if you remember this iterative thing, okay, so there's kind of the linear solver that takes into account the physics and also will enforce data consistency. I mean, consistency with the data. And now what you can see, the loop, you have like a linear step and then this proximal operator. And in fact, the idea is to replace the proximal operator by a convolution neural network that would then indirectly impose some regularization, because in fact, this can really be seen as a denoising step. There are quite a few works here, including by our group, now that have incorporated neural networks in this ADMM loop, or it can also be a FISTA loop. And this, in fact, is better. It's more robust than the feed-forward only neural network because it enforces consistency on the data, and is a kind of mix between you know, second generation methods. So we can really like build on all the good stuff that was developed in the past few years. And usually signal processing people much prefer that than having a kind of feed-forward neural network. Now training, okay, you need to choose a cost. So usually people, at least when you do it first, you use signal to noise ratio, but you can also have perceptual loss. You need lots of training data. And so you need examples of, you know, like, let's say, filtered back projection plus the high resolution. And when I say filtered back projection, I mean, it can also be MRI. I mean, a lousy reconstruction of MRI using a kind of inverse Fourier transform, if it's a subsample. And you need the use of data augmentation, translation, rotation, deformation, because the back projection, no, the back propagation algorithm, optimization algorithm of neural networks needs many examples and iterations. Now, deep neural networks for bioimaging, biomedical image reconstruction. Now, in the past few years, I mean, there's been literally an explosion. There were a few special issues in IEEE transaction medical imaging. So X-rays, I mean, that's the work I described, and there's also work by others. And I must say that usually the first people who applied neural network to reconstruct special type of images got their papers in you know, good journals, like, for example, transaction medical imaging, magnetic resonance imaging. And so this is relatively recent. Then people, I mean, did it for cardiac MRI. For example, there's the team of Daniel Rückert, very nice work, Simon Arridge. In fact, many of those guys are very famous people, also in compressed sensing and image reconstruction, that adapted their algorithm to use neural networks. 2D microscopy, for example, OSCAN, and so here also a paper in Optica, it's a pretty high impact journal. Fluorescence microscopy, so the first who were doing this, like the team of Florent Hugh, they got it into Nature. Super resolution microscopy, Optica, etc. So diffraction tomography, Optics Express. So essentially here you saw a pattern. So I mean, everyone thought of using neural networks, and then there was a kind of race, and the ones that first applied it successfully to a given modality got a paper in a journal, and typically relatively highly cited papers because there's lots of activity there. Ultrasound as well. Okay, now let me maybe now comment a few of those algorithms. I think the algorithm by Hammernick, but this is really the group of Thomas Spock. And I mean, Thomas was really one of the pioneers, and he was essentially using the idea of the unrolling. And he has a very nice algorithm, in fact, where he's using also, he's learning the nonlinearity of the neural network. And he was the first to really, for example, for magnetic resonance imaging of, you know, demonstrating that these neural network type algorithms can give very substantial improvements. You know, as I showed you for the X-ray tomography, but for MRI, actually for MRI, it's super active and super crowded. I mean, almost everyone is trying to use neural networks to do MRI reconstruction. Then, of course, you can also do dynamic MRI reconstruction. And so there was like the group of Simon Arridge. And I must say, what they did, it's really, they use more or less our algorithm, I mean, the one of Kyung Jin, and they sort of applied it to dynamic MRI. And they also obtained very, very good reconstructions. And they were the first to do, actually not quite the first, there were also people in Stanford. I mean, a few groups in parallel, but I mean, this was very successful for dynamic MRI. Now, here's another example is, I think this one is pretty neat. It's in fluorescence microscopy. And so it's people like Florian Hug at the Max Planck Institute in Dresden. I mean, it's Martin Weigert is now at EPFL also, but I mean, the idea here is like microscopy, as Paul told you. I mean, it has a relatively good in-plane resolution, but it's very bad axially. Okay, so lateral is good, and axial, you have like this bow tie type blurring. And therefore, if you look at the 3D micrograph, you have good resolution in XY and very bad in axial. And so what they propose, in fact, is a system where that uses the good resolution in the lateral plane. So what they are doing, in fact, they take the data, and from the data, they will train a neural network that now from those lateral views, they will take patches, simulate the coarsening that would happen in the axial dimension. And so those would be simulated blurs in the axial dimension. And then they will train a neural network that take this blurred stuff and try to restitute this nice, crisp, you know, lateral images. And so, of course, they train it on patches lateral, but then they apply this algorithm on the axial planes, and they are really able to get much better axial resolution with their microscopy. Okay, so this is an interesting paper that actually made lots, got lots of comments that was published in Nature, where the people were super extreme. They said, okay, let's forget about the physics. Let's forget about everything, because machine learning can do everything. And let's just construct a neural network that goes from the sensor data. So they applied it, for example, to MRI. So from samples of the Fourier transform to directly reconstruct the image. But to do that, I mean, they have to do a fully connected neural network, like a few layers of fully connected neural networks, and then some convolution networks to reconstruct the image. And in fact, they demonstrated that this is completely feasible. So there's zero input from the physics. The machine learns everything. Maybe it learns that the MRI is doing an inverse Fourier transform, etc. And I mean, this kind of works. They published it in Nature, but people are extremely critical about this work. Well, first of all, it doesn't scale because what they reported is a reconstruction of 128 by 128 images. I mean, that's really tiny and it's only 2D. And they couldn't do much more because they have fully connected layers. And so the memory scales like n to the power 2D. So D being the number of dimensions. So in fact, if you wanted to do 3D imaging, there wouldn't be a computer large enough that you can actually store that. So it really doesn't scale well. And maybe also here, I'm not sure they did a really fair comparison with other methods that, you know, like use sort of what I was discussing, but nevertheless, they get published in Nature. Now, okay, all this is nice. Everyone is super excited, but I'd like to leave you with a word of caution. Deep neural networks can behave erratically. I mean, they can be completely unstable. And there's a very interesting paper by Antung Hansen. In fact, I just read his PhD thesis. Hansen, so they are at Cambridge University. And I think this paper has just been accepted in the proceedings of National Academy of Science. So I think it's an important paper. And what they demonstrated that actually these neural networks can be very unstable. And they did some kind of adversarial stuff that they create a small perturbation on the data or on the image, but it can also be on the data here, so that, let's say, visually it doesn't look very different. And now if you apply like compressed sensing, I mean, even with the perturbation, the compressed sensing, I would say like compressed sensing is relatively stable. It performs relatively well. But if you do with neural networks, I mean, if you can have super erratic reconstructions like here. And in fact, what they observed, this is interesting, they observed that because you always have those challenges, there's always someone that comes with a new neural network that does better than all the others, otherwise you cannot publish. Okay, so now what they found is actually the guys who do the better are usually the easiest to fool. Okay, they're less robust. And in particular, for example, this one, AutoMap, I mean, this one is one of the worst in terms of stability. And it's probably not so surprising because it's learned so much. And in fact, they didn't have like infinite data. So you know, you don't really know how it's going to behave on stuff it has never seen. Okay. So conclusions, frontiers in biomedical image reconstruction. So there are great opportunities for learning-based techniques. And because this will help us to do faster, higher resolution, lower dose imaging, the new can profit a lot from the old. In fact, this also, if you see historically how it developed, I mean, you can rely on first generation, also second generation when you put the neural network inside the loop. Now, the really important thing is, can we really trust the results of compressed sensing? Yes, because we understand what it does. Of deep neural network, this is much more delicate. And also, how do you assess reconstruction quality? So I think it should be task-oriented because signal-to-noise ratio is not necessarily relevant. So, I mean, the things we need to work on is improve the stability of those neural networks because it's super dangerous. In fact, people in machine learning, it's not only for image reconstruction, it's also for classification. They've seen that neural network can be fooled and you don't really have a guarantee of behavior. We also need a theory to guide the design. So what is the optimal architecture? So for example, if you do this unrolling, this gives you a nice framework. A theory also to explain the regularization effect of neural networks and their ability to generalize. Infrastructure requirement. Now this changes the rules because now you need very high quality data. Now to do machine learning, you need huge amounts of data, including gold standards, and also the development of more realistic simulators. So both ground truth images, physical forward model. And also, I mean, imaging is 3D, and you know, like neural networks like PyTorch, etc. They're, I mean, somehow applicable to 3D, but you can see limitations, so still missing. Okay, so that essentially gets me to the end of the tutorial. So let me just show you a few references now. I mean, those references here, the most important one is this paper here, which in fact is more or less the tutorial that we have been giving to you. So it's Biomedical Image Reconstruction from Foundation to Deep Neural Networks. So it's in Foundation Trends in Signal Processing. You can also find it on arXiv. And I also recommend this paper because they're all the references, okay, the references of important work. Now on this page, I'm mostly citing our work. I mean, also the work that goes with the presentation that I've been giving. So for example, here, this is for the theory of sparse stochastic processes. You know, this representative theorem to explain the sparsifying effect of L1, etc. So that's on the foundation side. On the algorithmic side, Paul has been describing to you the global bioimage library. And there's a paper also that was published in Inverse Problems that in fact explains to you a little the philosophy. And here's some other papers on application of the framework for doing like a sparsity promoting image reconstruction. But of course, I should not forget neural networks. And so this is, you know, the paper that, you know, we're very happy that, you know, hopefully, well, you know, that was rewarded by the Best Paper Award. And some other papers here, there's also like a review of CNN applied to image reconstruction problem, a kind of iterative version of a CNN algorithm, and even like a representative theorem for deep neural network. In fact, this one is interesting because we looked at the neural network like an inverse problem, and we have actually an algorithm for kind of designing the nonlinearities that also you know, relies on regularization. Okay, so this concludes the presentation, and of course, I mean, this is the work I've been presenting to you is not just our work. It's a really huge team effort. It represents maybe more than a decade of work in biomedical image reconstruction. There are so lots of alumni of the lab that have, some of which are now professors at the various places or postdocs, you know, members of the lab now. You know, that's the way we do now. I guess you too. We're confined, and of course the funding, ERC, and so in this case I was very lucky because I benefited from 2 ERC grants in a row. So the first was more like on the stochastics, and the second, which allowed me now to develop this software library. Okay, so this concludes it, and then we are ready really to answer your questions. And also feel free to, if you want, you know, some of the paper of the software, you can go to our website. So it's the website of my lab to gather the information. Okay, so bye-bye then.